My name is Andre Rosa. I'm a professor from Brazil, and I will guide this moment, this section. It's a pleasure to me to stay here. And we are starting the second day of the Eurasia Waste Management Symposium with the section 4, Biological Methods for Waste Treatment. First of all, I'd like to welcome you all. And previously, I apologize of my pronunciation to introduce someone during this section. And the first presentation will be guided by, just a minute, by Simone Paul. It is here, okay?
Can you hear me?
Ready? Okay.
Can you hear me?
Yeah.
Okay.
Thank you for presentation. You can share your screen, and I will introduce you. Simone Paul works as PhD student at National University of Galway, Ireland, in the microbiology department, and he receives his bachelor's in environmental engineering in 2015 and his master in technologies for environmental remediation in 2018 from Universidad della Studi di Cagliari. He works on biovalorization of food waste through lactic and acid fermentation. And thank you for presentation. You have around 15 minutes, and after we have the questions for the audience. Thank you, Simone Paul.
So good morning, everyone. My name is Simone Paul. I'm second year PhD student in the microbiology department of the National University of Ireland in Galway. My work is supervised by Professor Lenz and is about food waste bioconversion through lactic acid fermentation. During this presentation, I will give you some general information on food waste and lactic acid work, followed by other information on my PhD work in terms of objectives, methodologies, and results. To conclude with some partial conclusion and my future work. So I choose to work with food waste because nowadays food waste is both a problem and an opportunity. A problem for the amount of food waste that is produced globally in the world, that is almost 1/3 of the total food that is produced globally. This amount of food waste generate a lot of environmental impact, like the increasing of the greenhouse gases produced associated to the food waste, and moreover, the management strategies and treatment strategies nowadays are still not economically appealing, like composting and anaerobic digestion. For this reason, in this era of circular economy, food waste can be seen as the perfect platform from which we can derive energy and biomaterials. One of these biomaterials is lactic acid. Lactic acid has a strong increasing market that nowadays is worth 9.8 American billion and is used in several industrial applications like food and pharmaceutical industry, and moreover is the main component of the most produced bioplastic in the world, that are the PLAs. 90% of industries nowadays produce lactic acid through biological synthesis and through carbohydrate fermentation that can be performed by several microorganisms. The most important of them are the lactic acid bacteria, in which lactic acid is the main byproduct of their metabolism. Lactic acid bacteria can follow two types of fermentation pathway, the homolactic fermentation and the heterolactic fermentation. In the homolactic fermentation, from each mole of glucose are produced 2 mole of lactate through first the oxidation of glucose into pyruvate through glycolytic pathway that is then reduced to lactate through an enzyme that is called lactate dehydrogenase. The heterolactic fermentation instead is less efficient, with just 1 mole of lactate produced from every mole of glucose. Even if lactic acid industry is very consolidated, still present limits and problems. like the utilization of pure substrate, like glucose and xylitose, that increase the operational cost of the process. They still use a discontinuous system in batch with separate phases of hydrolysis and fermentation. And in the end, they use separation through purification that needs an expensive downstream process after the fermentation to obtain a pure and concentrated lactic acid, final lactic acid. So in my PhD, the objective is to define a new biorefinery configuration that operates in continu in order to improve the lactic acid production yields and the extraction and purification phase, trying to cut all the operational costs that are associated to both phases. For this PhD, I'm using synthetic recipe that try to represent the average household waste. It is composed mainly by vegetables and fruit, and in less amount meat, fish, and high carbohydrate ingredients like pasta and bread. As we can see from the table of the characterization, this food waste is characterized by high concentration of carbohydrate and less concentration of protein. The food prior the utilization was cooked, milled, and mixed, and stored at minus 21 degrees Celsius. So in this presentation, I will give you an overview of what I did last year during my first year of PhD. I performed some preliminary screening batch tests to investigate the role of the inoculum, pH, and pretreatment of the food waste to find the different pathways that are involved in the organic acid production, of course, with the special focus with the lactic acid and how these parameters affect the bioconversion process. I worked with 200 milliliter bottles, of course, using the synthetic food waste. With this initial data, 8 gram volatile solids of feedstock, 2 gram volatile solid of inoculum, 5 days and 37 degrees Celsius, so mesophilic condition. I used 3 different inocula, 2 anaerobic sludges coming from the 2 wastewater treatment plants here in Ireland, an aerobic sludge from an oxidation tank, always of a wastewater treatment plant, and then I included a case with no inocula and just food waste as control. Every of these sludge was tried in 3 different conditions. Initial pH 7 using a phosphate puffer, uncontrolled pH, and the third uncontrolled pH after a thermal pretreatment, 80 degrees Celsius for 1 hour. The analysis that I performed in this phase were total and volatile solid, soluble chemical oxygen demand, concentration of carbohydrate, lactic acid, and volatile fatty acids, and then the microbial community analysis. So in the first, this is the first case, pH 7. As you can see, the buffer worked pretty well. The pH dropped from 7 to 6 in 5 days fermentation. But as you can see, lactic acid was produced just in the beginning of the experimental phase, in the first 12 hours, and then it was converted in volatile fatty acids. As you can see, the development of the process was a mixed acid fermentation with acetate, propionate, and butyrate present in the same, almost the same concentration. The uncontrolled pH gave me different results. The pH dropped in a range from 4.8 to 3.9. In the 3 cases with the sludge addition, I had always the lactic acid was present in the first day of fermentation and then was degraded to form mainly butyrate that in certain cases represented the 80% of the soluble COD. Instead, the case with just food waste as control, as you can see from the blue bars, present on a good production and accumulation of lactic acid, and the final pH was 3.9, so below 4. The last case was with the pretreatment. Pretreatment gave me 15% more of initial carbohydrate concentration that were available for degradation. This pushed the pH to drop more. In fact, the pH in these 4 cases were from 4.5 to 3.3. The first 2 sludge, the granular sludge and the dairy gold sludge, presented more or less the same, results with the butyrate fermentation. Instead, the primary sludge in the bottom part of the slide, the primary sludge and the control with just the food waste had a good production and accumulation of VFA that was of lactic acid that was not converted in any other organic acid. In these 2 cases, the pH was 3.8 and 3.3. So other 2 cases with the pH lower than 4. The microbial community analysis show us that lactobacillus were present already in the food waste. So this means that potentially every case in the right condition can give us the lactic acid production, but the competitors that were introduced with a sludge push the degradation of the lactic acid in the other metabolites, especially with the presence of Clostridium that are responsible for the formation of the butyric acid, and Bacteroidales that are responsible for all 3 other metabolites, so acetate, butyrate, and propionate. So these results can be summarized in this pathway that we are proposing, that says that the best lactic acid production and accumulation occurs at pH lower than 4, and then that when the pH is higher than 4, lactic acid is yes produced, but also convert in other BFA that are mainly butyrate when pH is between 4 and 5, and a mix of butyrate, propionate, and acetate when pH is higher than 6. Other conclusion that we can have from this experiment is that the food waste showed already a good abundance of lactic acid bacteria, that the addition of external inocula introduced in the system some strong lactic acid competitors, like, as I mentioned, Clostridiales and Bacteroidales, that reduce the lactic acid production and converting it in other organic acid, and then that the pretreatment, yes, improved the initial carbohydrate concentration, but just 15%. That was not enough to justify the energy spent for the pretreatment itself. These experiments were taken as base to run these 2 reactors that are running right now in the lab, 2 USB operating in feedback, 1 liter. I'm making some tests to test the organic load rate and the HRT to improve the lactic acid yield production, and they both running at pH 3.8. So the very acidic environment that I found that was more suitable for lactic acid in this batch test. As a future work, I'm going to make the transition in continue, and then next year I will be focused on the extraction system, and I will use membranes and perform some membranes efficiency test. Before to conclude, I would like to thank my team, my supervisor, Professor P.N.L, and the committee and the organizer of this symposium for letting me share my results for the first time in front of an audience. Yeah, for the first time in front of an audience. Thank you.
Thank you, Simone. Okay, with the time, and if someone would like to ask Simone Poe about some question, please, you can write the question on chat, please.
Was I in time?
Yeah, yeah.
Okay.
Congratulations. It's so difficult to do this, I know. I have a question. It's so
Yeah.
interesting, your research, and
Thank you.
you studied about the bioconversion through lactic acid fermentation.
Yeah.
And for example, you talked about acetic acid, about the some substance during the process. And have you monitored the biogas production, because it's a fermentation? You have some. You are studying the energy potential, the possibility to use the system. What about the biogas?
I measured I was monitoring the biogas in the 12 cases that I showed you. I didn't reach very good yield of biogas, not methane, because the pH was really low for methane production. So all the methanobacteria I had in the microbial community analysis were basically inhibited. And most of the gas was composed by CO2. And also I didn't found lots of gas, because 5 days fermentation is very low time to let the gas form, especially for yes, methane. Even in the cases I performed with a buffer that was pH 7, that is more suitable for methane production. I didn't find any methane because the experimental time was very short.
So you don't recommend the biogas as a control variable for this situation?
Well, I can recommend, but well, I'm more interested in organic compounds, because they are more economically valuable than methane.
But with waste, I worked with waste, and probably you need to use the biogas, the biogas production. But okay, for this, more questions. Anyone would like to ask Simone Paul? Okay, here we can finish your presentation. Thank you a lot.
Thank you so much.
Congratulations for your research. Thank you.
Thank you.
Now I would like to introduce the second
Rosa.
Presentation. Hi.
Rosa, Mr. Khaligh and Mr. Altınbaş is not here, so we will continue your presentation.
The second isn't here, okay?
Yes.
Okay, so we can go to the third. That's it's my presentation in this case. Study of properties and energy potential of malt bagasse produced in breweries. I'll share the presentation with you. I will. Just a minute.
Yes, Ruda Salimi.
I think the second presentation is my presentation. Sude and Dr. Mahmoud Altınbaş.
Just a minute. So the second one is here.
Yes.
I'm sorry. So thank you for your presence and your presentation. Sudi Salim, I'll introduce you. Just a minute. Sudi Salim is a project assistant and PhD student at Istanbul Technical University, and she receives her bachelor in cellular molecular microbiology from Iran and her master in environmental biotechnology at 2015 from Istanbul Technical University, Istanbul, Turkey. Thank you for your presentation. You have around 15 minutes, and after, some questions. Please, you can share your presentation.
I cannot share it.
You can share now.
Because I think I need to stop my.
Okay.
Okay. I think now it's available. Okay.
Is it okay now?
Yes. presentation for you.
Good morning, everybody. My name is Sude Salimi. I'm doing my PhD at Istanbul Technical University in Environmental Engineering Department, Environmental Biotechnology Program. I'm going to give a presentation about valorization of food waste by oleaginous yeast. I will give you a brief background about why we use food waste and why we choose oleaginous yeast. I will explain how I applied fermentation method to increase solubilization of food waste and how I applied the output of this fermentation step as growth media for growth of oleaginous yeast under different environmental conditions. Then finish with results and conclusion of the study. Nowadays, because of global population and also rise of economy, amount of generated municipal solid waste is enhancing day by day. In past 3 decades, generation of municipal solid waste enhanced more than 4 times, and 1/3 of this waste is food waste. Food waste include waste during preparation food, cooking food, and uneaten food. This waste is rich in organic carbon, minerals, proteins, and fatty acids that considered as valuable feedstock for valuable microbial products. By increasing energy demands in the world, it is necessary to find an alternative energy source to meet these demands. Applying different microorganisms as a renewable source is a method to consume complex organic matters and recovery of valuable products as biofuel besides treatment of waste. On the other hand, oleaginous yeast as sustainable source for lipid production, they are sustainable source for lipid production because they have ability of accumulate lipid more than 20% of dry mass inside the cell. Biovalorization of food waste is more effective if organic matters became soluble. There are some different treatment methods to improve solubility. Fermentation is considered as an ideal biological pretreatment to enhance solubilization of organic matter. The objective of my study is first investigate the effect of 2 different anaerobic microorganisms groups like cow manure and cow rumen on fermentation of food waste. And secondly, evaluate growth of an oleaginous yeast named Yarovia lipolytica on fermented food waste in different pHs and different mixing RPMs. We collected food waste from dining hall of campus of Istanbul Technical University. The waste contained cooked and uncooked waste, grinded and dried at 7 degrees. Dried waste passed through filter to have parts less than 3 millimeters, and then we store it at 4 degrees. We used Yarovia lipolytica strain MUCL 28849, and we used YPD agar media to store the strain at 4 degrees. For anaerobic fermentation of the waste, we ran a 20 days batch experiments under thermophilic condition and natural pH with solid retention time of 5 days. We applied 2 different microorganisms groups to find the optimum one. Then fermented food waste was collected and pre-treated for incubation of Yarovia lipolytica in all the next steps. Fermented food waste with different dilution rates was applied for cultivation of the yeast to find the optimum dilution rates. Then batch cultures was run with different pHs and different mixing RPMs to select the optimum condition for the growth. The picture with dark brown media shows our fermented food waste before yeast cultivation. The other one with yellow color media is the media after cultivation and after growth of yeast inside it. In fermentation with 2 different microorganisms groups, after 13 days, we can see that soluble COD reached to its maximum amount, around 53,000 milligram per liter when we applied manure, and reached to 60,500 milligram per liter when we applied rumen, and get stable after 13 days. So results confirm rumen is more effective inoculum in fermentation of food waste and in solubilization of food waste. In this step, fermented food waste was collected for cultivation of the yeast in all the next steps. Food waste fermented by rumen contain 181 millimolar volatile fatty acid, consists mostly acetic acid. Ratio of carbon to nitrogen was around 65 with pH of 4.8. When different concentration of fermented food waste was applied, we can see that by increasing the concentration, the growth was increased also. We monitor the growth every day by measurement OD of media. When it comes to the sample with no dilution, we have the highest growth with measured OD of around 24. It shows food waste has no inhibitory effect on growth of Yarovia lipolytica and can be applied without any dilution and directly as growth media. In next step, I selected 4 different pHs from 5.5 to 7 and 2 different mixing RPMs as 100 and 150 to evaluate the effect on growth. This graph shows the growth on 100 RPM. During growth, pH always increase because of volatile fatty acid consumption in the media. So we always control and adjust pH every day by adding one normal sulfuric acid to the media. The highest growth and also highest generated biomass, as I will show in next slide, belongs to pH 5.5. Here, when we increase the RPM from 100 to 150, again, we have increasing growth. The optical density increased from 24 to 30, again for pH 5.5. For the other pHs, there is also a small increase, but for lowest pH, it is more considerable. Generated biomass was also increased by changing pH, by decreasing pH, and also mixing RPM, by increasing mixing RPM. When we leave media with its natural pH without any control and without any adjustment, the VSS concentration was around 4,800 for mixing RPM of 100 and 6,500 for mixing RPM of 150. But when we apply different pHs, we can see the highest biomass concentration in pH 5.5 and RPM 150. Here, the VSS concentration increased to around 8,000 when we applied pH 5.5 and mixing RPM of 150. So all the results shows the food waste as suitable substrate for oleaginous yeast Yarovia lipolytica. There is no inhibitory effect, and it is possible to apply it directly with no dilution. When pH 5.5 and 150 mixing RPM was applied, growth increased considerably. That is in accordance with other studies, because the optimum pH for growth of this yeast is less than 6 based on references. So these data will be used in our next experiments with the aim of increase lipid storage inside the cell of the yeast and evaluate the storage lipid composition as an alternative for biofuel. Thank you so much for listening my presentation.
Thank you a lot, Sudi Salimi, for your presentation, an excellent presentation. And here on chat, we have a question. The question is from Simon Odmi. I have general questions to the speaker. What is the difference between SCOD and TCOD? How they differ? How they differentiated?
Yes, TCOD means total COD, total chemical oxygen demand. SCOD means soluble chemical oxygen demand. When we measure total COD, we have all of the suspended solids and all the particles inside our media, and we use it directly for COD measurements. But when we apply soluble COD, we pass the media through 0.45 micrometer filter, and we collect the filtrate part without any suspended solids inside it. And we measure the COD of just soluble part of the media. So the soluble COD is always less than total COD.
Thank you for the answer. More questions? I have a question. Congratulations for your research, so interesting. And you work with microbiology activity, okay?
Yes.
Yeah, and you study, for example, the rotation, the difference, the rotation level, the influence in the activity. What about the temperature? Did you study this variable?
We applied directly temperature of 55 degrees to have the better generation of volatile fatty acids and to inhibit the growth of methanogenesis. So for both of the microorganisms, we applied the same temperature as 55 degrees.
Okay, more questions? Okay, thank you a lot, Sudi Salimi, for your presentation.
Thank you.
You can stop sharing your screen. And the third presentation, it's an article that I'm an author entitled Study of Properties and Energy Potential of Malt Bagasse Produced in Breweries. So I will share my presentation, just a minute. It's okay, the presentation. Everyone can see.
Yes, we can see.
Okay. So I'll present this article entitled Study of Properties and Energy Potential of Malt Bagasse Produced in Breweries. I'm André Rosa. I'm professor at Federal University of Viçosa from Brazil. And the other authors of this research are André Soares and Gabriel Côrtes. And here we have the beer, that is the main product of the beverage industry, with a significant increase in its production in recent years, especially in Brazil, that we have the largest producer of this material, this good, in Latin America, and we are in the third in the international ranking of beer producers. Because of this, we have a high generation of waste from this kind of industry, and the main beer byproduct is the malt bagasse, with 85% of the volume produced in this activity. The malt bagasse is composed by fermentable sugars that requires rapid removal or treatment of the residue. So we need to offer alternative disposal or treatment quickly. And the beer is the main products of the beverage industry in our recent years. Some useful alternatives to disposal this material is, for example, to direct disposal in the soil or in the landfills, but we have problems with the high pollution potential of the leachate from this material, and the food substance in livestock that in Brazil it's common, but now we have restrictions according to some rules. A processing of residues for biotechnological processes is a trend to aggregate value of materials, mainly as alternative sources. And here we can point out the thermochemical processes that we have some alternatives for energy production using malt bagasse as biomass. In this sense, characterization of biomass becomes essential in order to apply, for example, thermochemical process or another alternative. So this work aimed at characterizing the energetic properties of malt bagasse produced in a brewery, as well as to compare it with other biomass. Material and methods, characterization of malt bagasse. The characterization was carried out by using 10 samples from a large brewery with a Pilsen type. We collected 1 kilogram for each sample during this period. This period was monitored in this brewery, and the moisture and the mediate composition. In this case, mediate composition, we studied the fixed solids, volatile materials, and ashes. Followed this methodology. The elemental composition, we used this equipment, and the real higher calorific value was determined using this calorimetric pump. The table 1 indicates the calculation procedure for determining the theoretical higher calorific value and lower calorific value. So we studied the theoretical and the real calorific value, especially higher. And here the theoretical, higher calorific value theoretical was calculated by using the results from fixed content, volatile content, and ash content. And theoretical lower calorific value, we used these equations. A survey of beer and malt bagasse production data was carried out in addition, and after an unitary relationships were determined associating mass balance production and energy production. Some results of the research, the potential of energy generation from malt bagasse. Here we have a descriptive statistic of characterization of this residue. Here the number of data from the 10 samples with moisture, calorific value. The immediate analysis, we had 6 samples with this mean and median values. Here we have a moisture around 8%, and calorific value, the higher calorific value, here we don't consider the moisture, was around 21.3 megajoules per kilogram, and the lower calorific value, here this energy considers the moisture of the material, the value was around 2.3. In general, the material is homogeneous because of the standard deviation don't have high values, and immediate analysis is compatible with other biomass sources as a coffee parchment. Here we have the the values that are compatible with our results, corn cob and sugarcane bagasse, according to this research from Paula et al. About the elemental composition, the carbon composition was almost the half of the composition of the material, 49%, oxygen 37.5%, hydrogen, that is so important in this energetic issues, 7.9%, and nitrogen 5.7%. The hydrogen content, as I told, could be associated with the calorific value of biomass, especially when we analyze the lower calorific value. The hydrogen content is so important to increase the energy potential. And our results was higher than coffee parchment with 6.8% when we are talking about hydrogen. Sugarcane bagasse, 6.8% of hydrogen too, according to this research. Here the comparison between our material, malt bagasse, with other biomass resources. The figure 1 presents the correlation of the atomic ratios of hydrogen and carbon and oxygen and carbon for bagasse, malt bagasse compared to other biomass sources. Here is the name of this analysis is the Van Krevelen diagram, where we study the ratio between hydrogen and carbon and oxygen and carbon. In this situation, the best characteristics to recover the energy from a residue is when the ratio hydrogen carbon is higher and less oxygen and carbon. So we are in a good region of this diagram in comparison with other biomass resources. And about the higher calorific value and the lower calorific value, we studied the theoretical using some equations and the real values for the malt bagasse. And here we have the results where in the higher calorific value theoretical, the value was around 21.3 megajoules per kilogram. And the lower calorific value, using here the real situation associated with a higher calorific value obtained in the calorific pump and the moisture of the residue, the energy produced was associated with 2.3 megajoules per kilogram with moisture of 8.4%. In general, the values obtained in laboratory real data were slightly higher than those estimated, in this case, the theoretical values. About the potential of energy generation, here we have 78% of the moisture. If we dry this material, for example, having a final moisture of 50% for malt bagasse, the lower calorific value could be achieved 8.9 megajoules per kilogram, close to the can bagasse with this value, 9.5 megajoules per kilogram, evaluating a similar moisture. And if it's possible to improve to heat, in this case, drying this material up to 15% of final moisture for malt bagasse, the lower calorific value could achieve almost 17 megajoules per kilogram, close to other sources of biomass of agricultural origin. So the drying or the hydration of this material could offer a technical feasibility and its adequate use as an alternative fuel. So we have the potential, but we need to improve or to offer heat and in order to valorize this material. Some unitary relationships and the energy potential in the brewery sector. using the real data from the brewery that we monitored, we calculated some unitary relationships as mass of bagasse malt per volume of beer produced, energy generation potential per volume of beer produced, and energy generation potential per mass of bagasse malt generated. And here are the units and the values presented here. According to these results, we can point out that the average production in this brewery was around 500,000 hectoliters of beer, 6,000 tons of malt bagasse per month, a generation of 12 kilograms of malt bagasse per hectoliter of beer, and the energy potential for this residue in this brewery was around almost 14 terajoules per month, which could be used, for example, to generate energy in boilers. So in general, this material is dispatched, for example, in the landfill. We don't recover this energy. The main conclusions of the work: malt bagasse presents homogeneity for chemical and physical characteristics beyond good calorific potential, favoring its use as biofuel. The high moisture of the residue in nature limits it energetically, making it necessary to produce the residue for a large-scale use. The malt bagasse presents energy characteristics that justify more investments and research on energy recovery in benefit of breweries, which have high energy demand in the production process. And finally, the energy properties of malt bagasse are quite similar to those of other biomass of vegetable origin, and the high calorific value of malt bagasse stands out when compared with biomass evaluated under the same moisture conditions. This indicates the possibility of using malt bagasse in a similar way to residues such as sugarcane bagasse, which is already burned on a large scale for energy production in the sugar alcohol industry. Here's some reference of the presentation, and thank you for your attention. I'll stop share my presentation. Some question. The difference between high calorific value and lower calorific value is large. The moisture is the main reason for this difference, because when we are talking about the energy, available energy, we have a value, for example, we can obtain from a calorific pump, the higher calorific value. But to study the energy produced with this heat, the material don't have moisture, no water. But this isn't the reality. So the material in natura has a specific moisture, and because of this natural moisture of the material, the lower calorific value or the net energy that we can recover from this material is much lower. It's okay? But the moisture is the main parameter that influences this result. Another question? Okay, let's finish and go to the next presentation. If nobody has anything else to add, let's move to the next presentation that will be conducted by, who will be the presenter? It's here.
I think I'm John.
We will continue with Bernaniş or Kaya-Özsel.
Ben anlatayım.
Okay.
It's here, okay. I'm opening the here in the file that I received. I don't have your curriculum. If you could you introduce yourself, please?
I'm Berna from Bursa Technical University, Chemistry Department. Today I'll present comparison of hydrolysis and conversion of wet straw and cotton linter to platform chemical in various co-solvent water medium. The aim of the study is to compare the effect of solvent type on conversion of wet straw and cotton linter into key platform chemicals. Firstly, I'll start to describe biomass. It includes all of the Earth's living matters, plants, and animals. Biomass is renewable and sustainable source. It doesn't generate environmental pollution and it's carbon dioxide neutral. It's environmental friendly and has no greenhouse effect. Also, it limits the use of non-renewable sources. It's storable, and the most important thing is it has low cost. In this study, we used two different type of biomass. Wet straw is one of the most known agricultural crop, and it's a lignocellulosic type of biomass. Cotton linter is short, thick-walled, curly, and cylindrical fibers. It's an important byproduct of textile and oil industry, and its only raw material, which cellulose purity is 80%. For conversion of biomass to key platform chemicals, first step is degradation of the rigid structure, which composed of cellulose, hemicellulose, and lignin. In the second step, monosaccharides are converted to target products with a series of acid-catalyzed reaction. 5-hydroxymethylfurfural, furfural, and levulinic acids are important products. They can be used to obtain various chemicals such as used in many different areas, fuels, food additives, and pharmaceutics, and etc. 5-hydroxymethylfurfural obtained from glucose and furfural obtained from xylose. These are intermediate products and they can be converted to levulinic acid. Solvent medium is also important. Water is known as the greenest solvent, but sometimes we need other types of solvents. Organic solvent has a positive effect on both biomass solubilization and also product selectivity. Organic solvents are divided into three groups. These are polar aprotic, polar aprotic, and non-polar solvents. In this study, we used acetone as a polar aprotic solvent, which has higher effect than other types of organic solvents. Ionic liquids consist of a low melting organic anion and an organic or inorganic cation. Optimum solvents can be obtained by choosing perfect anion and cation for a specific area. This type of liquid can be used many different areas such as organic synthesis, inorganic synthesis, polymerization, and etc. In this study, we use butyl methyl imidazolium hydrogen sulfate, which is an acidic character. But the limit of these type of solvents are they have low cost. Deep eutectic solvents are alternative type of solvents to ionic liquids. These have low melting point, are obtained by combining at least two solids with a hydrogen bond donor and acceptor, such as urea and choline chloride. In deep eutectic solvent medium, biomass conversion is very slow due to its high viscosity. Therefore, the reaction time is longer than the other type of solvents. We used ethylene glycol and choline chloride with 2:1 mole ratio to prepare deep eutectic solvent in this study. In experiments, the reaction conditions are optimized for all solvents medium in our previous study. All reactions are carried out at 180 Celsius degree. For organic solvents and ionic liquids, reaction time is 30 minutes, and for deep eutectic solvents, reaction time is 2 hours. Optimum water co-solvent ratio depends on the solvent medium. Ionic liquids and deep eutectic solvents react as catalysts, so we used amber list conversion catalyst in organic solvent medium. For a general experiment, biomass and solvent put into the reactor, and it is heated at 180 Celsius degree during specified times. After the reaction, stainless steel reactor is cooled and mixture is filtered. Solid part used to calculate hydrolysis rate and liquid part used to determine products. Total reducing sugar content is determined with UV visible spectrophotometry, and other chemicals are determined with liquid chromatography. You can see the hydrolysis rate of wet straw and cotton linter from figure 3. The high hydrolysis rate is important in terms of the low amount of humins remaining at the reaction and the high amount of the monosaccharide passing into the solution. Wet straw and cotton linter solubility acts similar in different solvent types, but cotton linter solubility is very low compared to the wet straw due to the more rigid structure of cellulosic biomass. Total reducing sugar content gives the amount of sugar that remain without conversion as a result of the reaction. Wet straw's sugar content is higher than cotton except for the catalyst-free organic solvent medium. This can be related to the amount of the hydrolysis rate. You can see the amount of platform chemicals obtained from wet straw in figure 5. Ionic liquids gave the best result for all these chemicals. However, there is no big differences in the amount of levulinic acid between ionic liquid, deep eutectic solvent, and organic solvent with amber list. Choosing the deep eutectic solvent more reasonable when we consider the toxicity and cost. Figure 6 shows the amount of the platform chemicals obtained from cotton linter. Furfural is not found in the products since linter is cellulosic source, and furfural is formed as a result of the conversion of cellulose, which obtained by hydrolysis of hemicellulose. In addition, deep eutectic solvents appear to have a dominant effect on cellulosic biomass in obtaining levulinic acid. As a conclusion, in organic solvent medium, there is no there is no significant amount of product absence of catalyst. The presence of catalyst promotes both hydrolysis and product formation in organic solvent water solvent medium. The hydrolysis reached that in ionic liquid medium with catalyst loading. Lignocellulosic biomass solubility is higher than cellulosic sources in all solvent mediums, while a higher amount of product was obtained from wet straw in ionic liquid. Linter reached a significant value in this water solvent medium. Thank you for your attention.
Okay, thank you a lot for your presentation. An excellent presentation. Verena, questions? Anyone has question? Okay, so thank you a lot for your presentation. The next one, it's an article entitled Energetic Feasibility of Pouch Waste Used as Biofuel. As I'm an author, and just to follow the protocol, I'll introduce myself. I'm a professor at Agricultural Engineering in the Federal University of Viçosa. Rosa received his PhD in Sanitation, Environmental and Water Resources in 2013 from Federal University of Minas Gerais, and he is graduating in Environmental Engineering in 2007 at Federal University of Viçosa. So I'll share my screen with you. It's okay.
Yes, okay.
Okay, thank you. My name is André Rosa. As I told, I'm a professor at Federal University of Viçosa, and I will present the article entitled Energetic Feasibility of Punch Waste Used as Biofuel. The other authors are Gilberto Caldeira Bandeira de Mello, Wagner Luiz Santos, Arthur Lopes, and Stefan Gouveia Freire. The pouch is a material obtained from the waste empty rumens. Here we have, for example, in a slaughterhouse, where this material is removed. The ruminal content is the material inside this volume, and it is a most significant generated residue in slaughterhouses. We have in this situation a high moisture and difficulty to handle and store or dispose of it, composed of partially digested grass or dietary intakes of animal feeding and associated with constituents like urea and salts is the composition of the material. The production rate, it's a high value, in my opinion, around 23 kilograms per animal is slaughtered, according to this source. And in general, in Brazil, the destination is the landfills. If we evaluate a potential or a volume, production of this material, it's around 1,034 megatons per year in 2019, considering 45 million cattle slaughtered in this year, and the generation of 23 kilograms per animal, the production. So a big problem that we need to solve. According to this author, the characteristics of this material presents a 35.6 liters per animal, a high moisture content, around higher than 19%, 86.3% of volatile solids, 13.3% of fixed solids, associated with ashes, and chlorides contents of 93.4 megagrams per liter. Slaughterhouses are located close to the urban areas and have a small area for composting lanes and are distant from agricultural fields. So we need to think and try to find more possibilities to manage and to dispose of this material. As a consequence, the thermal process are a possibility in this situation. And the direct combustion, it's a possibility as an example of thermal process, but we need to evaluate the hazardous pollutants produced from this burn, because here specifically we have a big problem that in this material the cow eats salt as a supplemental alimentation, and this salt, when burned, when we offer heat for this material with chloride, we can produce dioxins and furans. But on the other hand, some benefits of this direct use are associated with the avoidance of methane formation in landfills, substitution of fossil fuels, and useful energy sources for abattoirs. So this study aimed at evaluating the energetic feasibility of paunch waste use as biofuel. For this, a comprehensive characterization of the paunch waste was carried out, as well as the assessment of air emissions from burning the residue, especially trying to evaluate the formations of dioxins and furans. Material and methods, the characterization of rumen waste. Here we have a schematic flow sheet of the slaughterhouse that was monitored, and some photographies. Here we have the stomach section, the rumen. After they open this this volume, this organ. Here they have output sieve, input press after this material is pressed with input, and after the output material that have a specific moisture that I will present. Composite samples were taken during 8 hours, and a subsample of 30 kilograms was collected, and after we approximate analysis and moisture was carried out. We evaluate this material, the obtained from output press, and we evaluate the elemental analysis was performed according to Parikh 2007, and a comprehensive characterization of rumen, evaluating the hydrogen content and the higher calorific value, following again these equations for the theoretical higher calorific value. Here we don't consider the real moisture of the material for this formula, for this equation, considering the immediate analysis and theoretical lower calorific value. Remember that lower calorific value, we consider the hydrogen and the moisture of the material here in this parameter R. Direct combustion tests were performed using 3 mixing options of rumen content with supplemental material that were compared 1:1, mass relation between the ruminal content and wood chips. We mix wood chips as a supplemental material 2:1 and 3:1, and here the reservoir and where the material was burned. And after some rumen wastes characterization, here we have the results. An average rate in our situation that we monitored, a production of 24.7 kilograms of pounds per animal. And this result was in accordance with Pacheco and this source that indicates a production that varies between a range to 26 kilograms and 23 kilograms. The table 3 results of approximate analysis and moisture over the waste treatment. Here we have the points, and this one is the output press, where we evaluate with more details. We did a comprehensive characterization of this material, and this material presented hydrogen content of 6.15%, a higher calorific value without the water influence, almost 18 megajoules per kilogram, and a moisture of this material was around 84.3%. That indicates a lower calorific value of only 0.7 megajoules per kilogram. The recommendation is drying to be used as an energy source, as a necessary alternative to use this material as an energy source. And energy potential, considering the 500 animals per day, that was the result from the monitored industry, could represent, in this case with this lower calorific value, a production of 9,000 megajoules per day of energy potential. Here are the combustion tests, considering the different proportions, the punch or ruminal content alone with what happened with when we burn just this material, and here this proportion. According to the results, we observed that the relation 1.1 showed the best proportion, because for the facility to start combustion was a visual evaluation, and keep it stable slowly a slightly higher calorific value. And the results of the the comprehensive evaluation indicates this, with the less moisture, 35.7%. In the sequence, in the industrial combustion and atmospheric emissions, the combustion test was carried out by using the proportion. So this was a pretest, and here a test with this proportion. That we used more materials. Measured values from this material that we used in this industrial combustion and atmospheric emissions studies was a material with a moisture 35.1% of moisture, volatile matter 74%, ash 9.4%, and fixed carbon 16.6%. A higher and lower calorific value on dry bases were 16.5 and 9.1 megajoules per kilogram, respectively. And carbon was the main composition of the material, 41.3%, and hydrogen, that is so important in energy recovery, the production of energy, 5.4%. The industrial combustion results, we monitored 9 parameters in these tests, and 2 parameters exceeded the limits proposed by Brazilian regulations. Here we have the values, and the standard in a regulation in Brazil was exceeded in particulate matter and sulfur dioxide, and for all other parameters the values were okay. According to these parameters, particulate material, the result was above the required standard, but in slaughterhouse, the installed dust collectors may solve the problem. So we don't have a combustion of this material, we don't have environmental control. So if we apply this solution, we can solve this problem. And the sulfur dioxide, the concentration was surprisingly high, even with sulfur content of 0.06%. A further confirmation is needed because we didn't understand properly this result. Metals, no problem with limits. Hydrochloric acid and free chlorine, no problem with limits. And this salt applied in the animal diets, it's not transferred to the gas phase during the combustion test. So this is a good result that we obtained in the research. And the chlorinate dioxin and furans, as a consequence of the chlorine composition content in the material, indicates that these pollutants were also below Brazilian limits. The conclusions of this research: rumen content presents homogeneity for chemical and physical characteristics beyond good calorific potential, favoring its use as biofuels. The results suggest that paunch waste, even given the chloride content, could be used as an energy resource. Its use as an alternative biofuel would reduce non-renewable energy sources or decrease the demand for other combustible materials, such as wood chips. And the thermal treatment of paunch waste would result in a reduction of mass disposal in the landfills, which represents a benefit to waste management. The authors would like to thank the financed institutions in Brazil, CAPES and CNPq, and some reference from the presentation, and thank you for your attention. Okay, questions, please. Table 4 is fixed carbon. Nitrogen content is lower. Table 4 is fixed carbon. Let's check table 4. Just a minute. I didn't understand about the table 4, but I'll check B. Nitrogen content is low, but air emission is high. I need to check the temperature. I don't remember. I didn't put this value in this presentation, but if you'd like, I can check and answer you, inform you. I can send if you the burning temperature. I don't remember. It was in my master 2009. I don't remember. I need to check the final material. And about the question A, what is the question? Could you help me to understand, please? Some would like to use the sound or rewrite the question, please, because I didn't understand. I'm sorry. Okay, I'm available to answer the question after the end of the section, especially the question A, okay? Thank you for the contribution associated with the question, and let's go to the next presentation. Dr. Adler, it's here.
I am here.
Okay, thank you.
Thank you.
You are welcome in the session. I will introduce you just a minute. Dr. Eleanor Adler is currently working as a research assistant in the Department of Environmental Engineering, Altınbaş University, Turkey. Adler receives her Bachelor in Environmental and Civil Engineering in 2008 and 2009 from Atatürk University, Turkey, and her Master and PhD in Environmental Engineering in 2013 and 2018 from Yıldız Technical University, Istanbul, Turkey. His research interest includes waste to energy, especially supercritical water gasification, waste and wastewater treatment, non-waste, contaminant transportation, SWOT analysis, MCDM analysis, risk analysis, and she's serving as reviewer of several international reputed journals. She has authored many research articles, conference papers, book and research projects related to her duty at the Environmental Engineering Department. Okay, thank you.
Thank you, Chair.
Presentation.
Thank you, Chair. It's okay?
Yeah, for me, yes.
Okay, good morning, everyone.
Okay,
good morning, everyone. My presentation is about nuclear energy. My presentation content consists of nuclear energy, nuclear waste management, nuclear energy versus other energy resources, bibliometric analysis, and conclusion. Nuclear energy has used since in the late 19th century, especially in military area. After 1970s, interest to its using increased. Uranium, thorium, and plutonium are used as fuels. Plutonium is produced from uranium and it can be used as a nuclear weapon. There are more than 440 nuclear power plants in the world. USA, France, Japan countries have the most nuclear power plants. In Turkey, 2 power plants are in the construction phase. 1 nuclear power plant is in the planning phase. The first nuclear reactor used in 1942, commercial reactors are divided into 2 groups as fast and thermal. Thermal reactors are more commonly used than fast reactors. Pressurized water reactors are the most used group from thermal reactors. Operating conditions are 15 megapascal and 320 degrees Celsius. In these reactors, uranium is enriched by 35% and water is used as cooler. The appearance of the nuclear reactor is as in the picture. It consists of retarder, cooler, control rods, reflector, reactor heart, and protector. Today, 2nd and 3rd generation reactors are operated. Third plus generation reactors have begun to be used with the development of 4th generation reactors or with the use of fusion reactors rather than fission. It would be a more attractive alternative because fusion reactors prevent to use nuclear weapon, and 4th generation reactors have less risk than fusion reactors. Safe management of nuclear waste consists of collection, separation, packaging, conditioning, storage, and disposal. Conditioning is done by concentration, solidification, compression, and incineration according to waste form. Waste are found in solid, liquid, and gaseous form. According to radioactivity content, they are grouped as very low, low, medium, and high levels. For storage, it's used an abrasion-resistant, safe, and sheltered structure. For very low level waste, can be used surface disposal facilities. For low and medium level waste, can use near surface, medium, and deep disposal facilities. High-level waste are disposed only in deep disposal facilities. Low and medium level waste can be disposed of well type, but high level waste cannot be disposed well type. Gas or liquid waste having low radioactivity content can be released directly into the environment. Decreasing volume for low-level solid waste is used compression and incineration methods. For liquid waste is used evaporation and drying methods. High-level waste are stored either by dry wet storage or after vitrification. Vitrification method is a difficult and costly option. France, Germany, England, Russia, Canada, Japan countries have active recycling facilities. Nuclear energy alternative has many advantages. It has not a greenhouse gas effect. It has high efficiency. For example, all of Turkey's energy needs can be achieved by 26 nuclear power plants. Nuclear energy reactors have long operation life. It can be reused after decreasing the radioactivity content of waste. The probability of an accident is low. It can be operated day and night regardless of climatic conditions. Uranium is found in many countries, is local sources. Less solid waste is produced. Like any alternative, it has some disadvantages. Radiation harms to environmental and people. Waste management is difficult and expensive due to the radiation content. To reduce the radioactivity content of waste, it must be stored for a long time, and this requires a lot of space. Plutonium produced plutonium can be used as a nuclear weapon. It has a serious impact as a result of an accident. It affects a large area, so more than 50% of the public don't accept it. Also, having high investment cost. Despite its negative aspects, it's a technology that continues to build. Looking at the literature, these accidents realized as a result of some precautions that were not taken, or natural disasters such as earthquakes. For example, in Chernobyl accident, the reactors did not have a protective shell. Fukushima accident happened due to the earthquake. The big effect was as a result of this accident because some reactors did not have a cooler. Nuclear energy is not a renewable energy source, but only water vapor and hydrogen are formed. So there is no greenhouse gas effect. Nuclear energy was compared to other commonly used energy sources. Looking at the table, we can see that nuclear energy has high efficiency, low pollution, and low fuel cost. Hydraulic, wind, and solar sources have low efficiency. It was realized bibliometric analysis about nuclear energy by using Web of Science. For this aim, nuclear energy, environmental studies, and waste management were used. The results obtained are shown in figure. In 1975, scientific studies had started to publish. There are above 105,000 studies about nuclear energy. Since 1980, approximately 3,100 environmental studies have been realized. 815 of environmental studies are related to occupational health and safety. Approximately 900 studies related to waste management have been carried out until today. These studies has done in mainly USA, Germany, Japan, France, England, and China. 30% of the studies were carried out in the USA. As a result, nuclear power is an attractive alternative for electricity production. It should be operated by experienced people by taking high precautions. Its use as a nuclear weapon should be prohibited. Also, for generation reactors should be developed, and fusion reactors should be selected. Considering the bibliometric analysis result, it can be said that more attention should be paid to waste management and work safety issues. Thank you for your attention.
Thank you, Dr. Elanu
You are
Ada.
welcome.
Okay, thank you. Questions? Just a question from Brazil, and here I think we have 1 or 2 units that produce nuclear energy. What about the Turkey? How important is this energy in your energy matrix?
I think Turkey has two nuclear power plants, construction phase, and one nuclear power plant is planning phase. For no, it has no operating plant. Maybe it can be used by operating experienced people and taking high precautions. That's it.
Okay, thank you for the
welcome.
information. Here we go to the next presentation. Thank you.
Thank you.
Dr. Elanu Ada, for your presentation. The next one, the valorization of ligneous cellulosic waste is the presenter. It is here.
Yeah, here.
Okay. Thank you for your presentation. I will introduce you. Dr. P.N.L was graduated from UDIS Technical University in 2012. She finished her PhD study on the algal bioprocess and nanoparticle production in this university at Bioengineering Department in 2019. She is interested in the algal bioprocesses, algal biofuels, nanotechnology, thermal conversion technologies, energy and the environment, and biotechnological applications. Thank you for your presentation. You have around 15 minutes.
Okay, thank you. Hello, I'm P.N.L from UDIS Technical University Bioengineering Department. I'm going to present our study on valorization of lignocellulosic wastes for solid acid catalyst production and its application in biodiesel production from algal oil. In recent years, the rapid depletion of fossil fuels, increasing energy demand, global warming, increasing price of fossil fuels depends on economic and political behaviors, increased orientation to alternative energy sources. In this context, biodiesel, which is one of the renewable alternative energy sources, draws attention because of its useful features such as easily biodegradable and environmentally friendly. However, biodiesel production from oil crops doesn't meet the required demand of vehicle fuel, and recently it is not economic and feasible. So it needs to be improved to produce more economically to be able to compete with diesel in the market. Vegetable oils and crops, which biodiesel produced from, are a kind of human food sources, and the shortage on food source causes to go up prices and make the biodiesel high priced. Algae having come into prominence over the last 2 decades as third generation biofuel feedstock with their appropriate structural properties and high production capacity. Algae can be used to make biodiesel because they produce large amounts of oil, and also once harvested, this oil can be converted into fuels for transportation, aviation, or heating, and they have high growth rate, and they can easily be cultivated. However, despite of their great potential, obtaining algal biofuels and other products requires more energy and input, and their production processes are quite expensive. To overcome production costs, researchers are investigating cost-effective downstream processes or reusable materials to use in algal biodiesel production. Biodiesel is a biofuel obtained after transesterification of raw materials such as vegetable oils, waste frying oils, and algal oils using homogeneous or heterogeneous catalysts and monohydric alcohols like methanol or ethanol. Heterogeneous catalysis using a solid-based catalyst for the transesterification shows similar properties as the homogeneous-based catalysis, such as mild operating conditions, a fast rate of reaction, and a high conversion. But the most important thing, the heterogeneous nature of the reaction means that no separation is required, and the catalyst has the potential to be reused multiple times. So heterogeneous acid catalysis is a promising alternative to conventional biodiesel production due to the simplistic and environmentally friendly nature of the process. Biochar is a solid product having high carbon content and obtained by thermal decomposition of organic materials subjected to low temperature in the absence of air. Various organic materials can be used for biochar production like woolly material, algae, grasses, corn straw, peanut shells, sorghum, olive piece, bark, and sewage wastes. Although being a solid biofuel, biochar has many application areas like environmental and agricultural practices such as soil amendment and water contaminant removal. Also, it can be utilized as catalyst for certain catalytic reactions such as transesterification and hydrolysis, which require so strong acid size. Solid acid catalyst production started with firstly biochar production in a pyrolysis reactor. After that, biochar treated with concentrated sulfuric acid for sulfonation step. After sulfonation, obtained catalysts were washed and dried to use in the biodiesel production. In this study, common lignocellulosic wastes from Turkey were valorized for solid acid catalyst production and are utilized in biodiesel production from algal oil. In this context, olive stone and walnut shell were chosen for solid acid catalyst production, and biodiesel production using solid acid catalysts were investigated statistically. In our experiments, olive stones and walnut shells were dried in an oven at the temperature of 100 degrees Celsius for 24 hours. After drying process, biomass was stored in an airtight container. Carbonization process were performed in protherm model split type furnace under the conditions of at two different temperatures as 500 degrees Celsius and 600 degrees Celsius, 20 degrees Celsius per minute heating rate, 30 minutes retention time, and 300 milliliter per minute nitrogen flow rate in order to provide oxygen-free environment. After biochar production, to obtain solid acid catalyst, sulfonation was carried out. This was performed by subjecting 1 gram of biochar with 10 liters of pure sulfuric acid. The mixture was heated at the temperature of 100 degrees Celsius for 5 hours. Then mixture was cooled to room temperature and washed with hot deionized water to remove the free sulfate ions. Washing was carried out until the pH of the filtrate becomes 7. After that, biodiesel production was performed using the solid acid catalyst with the amount of the catalyst varying from 1% to 5% and having methanol oil ratio ranging from 6:1 to 12:1 at the temperature of 65 degrees Celsius for 30 to 60 minutes using an ultrasound bath. And ice bath was used to cool the product, which composed of methyl ester glycerin mixture obtained at the end of the reaction. After the cooling, centrifugation was performed at 5,000 RPM for 5 minutes and created two phases as bottom and supernatant. For the characterization, FTIR, approximate analysis, sulfonic acid density, and GC were performed. So let's see the results. Firstly, we characterized biochar and biochar-based solid acid catalyst. As you can see, with the increasing temperature, the biochar yield decreased. This was expected due to the secondary decomposition of the material. Also, you can see that the moisture and volatile content, while moisture and volatile content decreased, ash and fixed carbon was were increased due to the removal of volatiles. After that, we measure the sulfonic acid density of olive stone and walnut shell biochars. And we found that the highest sulfonic acid density of 0.35 millimole per gram was obtained for the walnut shell, which was carbonized at the temperature of 500 degrees Celsius. With an increase in pyrolysis temperature, the sulfonic acid density decline was observed irrespective of the feedstock, as complete combustion and aromatization at high temperature often results in lesser number of acidic functional groups on the surface. Also, high pyrolysis temperature results in increased cross-linking and enhanced degree of polymerization, which might not result in formation of polycyclic aromatic sheets to trap the sulfonic acid sites. Also, you can see the sulfonic acid functional groups with the FTIR spectra, like here, as peaks occurred with the olive stone and walnut shell acidic catalyst. For the last part, biocell production from algal oil. Here, since the walnut shell solid acid catalyst has highest acid density, biocell was carried out using this material. It can be seen from the statistically obtained equation. The effect of reaction time is the highest. And we can say that all parameters here, time, catalyst oil ratio, and methanol oil molar ratio, has positive influence on the biodiesel yield. The main part, the reusability of catalyst, the yield of biodiesel was evaluated taking 5% of sulfonated walnut shell solid acid catalyst with 12:1 methanol oil ratio for 60 minutes, 4 cycles of transesterification. Yield was gradually declined from 82% to 72% after the 4th cycle of usage. Nevertheless, the durability of the catalyst is evident from its stability. In this study, olive stone and walnut shell were valorized for solid acid catalyst production, and walnut shell catalysts, which have higher sulfonic acid density than olive stone, was evaluated in the biodiesel production from algal oil. Since these materials are commonly found wastes, valorization of them as biochar, activated carbon, or solid acid catalyst for the usage in fuel production, water treatment, or agricultural application is very important. Solid acid catalyst can reduce the biodiesel production costs as well as the environmental impacts associated with the corrosive chemicals. Thank you for listening.
Thank you for your presentation. Questions? Anyone has questions? Okay, thank you a lot for your presentation.
Okay, I thank you. All right.
Okay, thank you. Now we are going to the last but not least presentation that will be presented by Mehmet. It is here.
I'm here.
Okay, I'll introduce you. Just a minute. Mehmet studies in bachelor degree at Yıldız Technical University in Environmental Engineering Department. He was completed his internship at Muski Marmaris Wastewater Treatment Plant. You are welcome to this section. You have around 15 minutes. Okay, thank you.
Thank you very much, Mr. Rosa. Good morning. First of all, I want to thank you all for your participation. This is Mehmet Uğuryaver. I'm an undergraduate student in Yıldız Technical University, Environmental Engineering Department. I'm here to present our study entitled as Biomethane Production Potential of Sunflower Straws, the case of Turkey. We prepared this study with Dr. Hülya Civelek, Yörükli, and Deniz Çınar. It's my first presentation on a symposium, so I feel so excited today. In this presentation, firstly, I will introduce solution of renewable energy production. Then I will give information about source selection. In materials and methods section, I will talk about Turkey's sunflower production. I will explain our calculations on formulation of sunflower straw. And finally, I will share our results. It will be explained that how much biomethane production from Turkey's potential. In the last centuries, the energy used to meet the increasing population and their demands has generally been obtained from fossil fuels. However, the depletion of fossil fuel resources and the fact that fossil fuel consumption causes many environmental problems. Biomethane production via anaerobic digestion is a popular solution to renewable energy production. Anaerobic digestion attracts attention due to its easy to operation and high energy recovery potential. Although many different substrate sources could be used to produce biogas, agricultural wastes are one of them with their high carbon content. The amount of agricultural wastes reaches millions of tons every year. Sunflower is an oilseed plant that has the most cultivation area and production in our country. Straws cannot be valorized such as animal feed due to its hard texture. Sunflower stalks are an ideal product to be used as a substrate in anaerobic digesters. The biogas production potential of the sunflower straws, when different pretreatments were applied, was evaluated and the theoretical biogas potential was not examined. The chemical formulation of sunflower straws was calculated and the theoretical biomethane production potential that could be produced according to this chemical formulation was calculated. Sunflower is an oilseed plant with the highest cultivation area and production in our country due to its high adaptability, its ability to be grown in dry and irrigated conditions, and its suitability for mechanization from cultivation to harvest. As you can see in the graph, there is a continuous increase in the sunflower production, except for minor changes. There is a correlation between sunflower production and the amount of waste generated, which is sunflower straw. According to the studies, minimum 0.7 tons of sunflower waste is formed for 1 ton of sunflower seed production. In that case, the dry weight of the sunflower straw produced in 2018 reaches up to 1,125 kilotons. Carbon, hydrogen, oxygen, and nitrogen are the required input elements for formulation calculation. Calculating the theoretical methane production of any substrate, it's needed to know the chemical components of the feedstock. The chemical composition of sunflower straw used in this study is given in table. As you can see in the table, half is made of carbon. Considering these element weights, the chemical composition of sunflower straw was formulated as carbon 45, hydrogen 63, oxygen 24, and nitrogen as shortened. The chemical composition of sunflower straw was multiplied with annual formation data, which is 1,125 kilotons. It was calculated that annual sunflower straw produced contains carbon, hydrogen, oxygen, and nitrogen elements. With knowledge of the chemical composition of a substrate, The theoretical methane production potential can be predicted from the stoichiometric formulation developed by Boswell formula. If the chemical formulation of the sunflower straw was used with the Boswell equation, 24 moles of methane can be produced from 1 mole waste. Theoretically, you can see the equation. Considering the molecular weight of the sunflower straws is 1001 gram per mole, which corresponds to 1.12 billion mole sunflower straw annually. 26.9 billion moles of methane can be produced annually from sunflower waste. From the ideal gas law, we could calculate the biomethane amount. Total theoretical biomethane yield reaches to 602.6 million cubic meter. You can see the equations and calculations also here. As a conclusion, in this study, the biomethane that can be obtained in the case of feeding sunflower straws to anaerobic digesters as substrate has been discussed, which is an agricultural produce in high amounts in Turkey. If the sunflower straws are completely broken down into biomethane, calculations have shown that 600 million cubic meter of biomethane can be obtained. Although the calculations obtained from this case study presents very high methane production potential, anaerobic system optimization and biomass to biomethane conversion rates must be determined with laboratory experiments. Thank you for your attendance.
Okay, thank you, Mehmet, for your presentation. Questions? In Turkey, is there any plant that do this, the biomethane production from sunflower?
For now.
Yeah.
Could you repeat the question, please?
In Turkey, is there any plant installed that produce methane or biomethane using this energy source, sunflower?
I couldn't see or I couldn't hear any operation about for that. But there is a very high potential on organic wastes in Turkey.
Mm-hmm. Okay. More questions? Okay, we finished on time the presentations. Thank you for your attention, and congratulations for the presenters to be on time. And I imagine I think that will be all for today. I don't know if the organization needs to say anything, but I think we can finish the presentations and stop this section. Okay. The organization would like to say anything?
Thanks for your participation.
Okay. So thank you.
The session.
Oh, and I imagine we can finish this section, okay?
Yes.
Okay, thank you. A good day for all. Bye-bye. Thank you.
Bye.